Hello, Hugo.
Can you see my screen?
Yeah, perfectly. Okay, Nisha, I think we're good to go.
Okay. So good morning, good afternoon, good evening, everyone, wherever you are. My name is Nisha. I work as a senior analyst in health and human services, and I'm currently pursuing my PhD at UT Austin, if you didn't know me already, from the IML-AI group. So today we plan to go over Matplotlib and the Seaborn library scripts that I've put together for today's session. So we have a lot to go over, so I'm going to try and split my time between the Matplotlib and the Seaborn notebook. I did send the link of the notebooks to Hugo, so if you want to follow along, he probably will share it with you guys. Otherwise, we can go over it as I am running through these scripts. So the main idea that I'm trying to get across today on these two libraries is how flexible they are, and when would you use Matplotlib versus when would you use Seaborn, and what are the advantages of using one versus the other. So Seaborn is essentially built on top of Matplotlib. So we are going to go over the Matplotlib first and then look at the Seaborn. Matplotlib essentially is a grandfather library, and as the name suggests, it was created mainly by another guy called John Hunter. He was replicate MATLAB, another programming language that is very well known for visualizations, especially in the scientific field. Even now, as I'm doing my PhD, many people still use MATLAB all the time, and it's free in universities for students, but outside of university, it's usually not affordable. That's why we want something similar to MATLAB in Python, which is what Matplotlib offers us. It is an excellent 2D and 3D graphics, especially used in the engineering domain. And the main pros of Matplotlib is that we can generate really easy, simple plots, and the customization is the key for Matplotlib. It gives you a sense of how much you can customize. That's the difference between this one and Seaborn. So many experienced data scientists comfortably use Matplotlib than Seaborn, because Seaborn comes with just one-liner. You can create beautiful plots in Seaborn, but if you want that customization, having some point or some outlier named a specific way, then Matplotlib is the way to go, I would say. So now that you have an idea of how Matplotlib works, and it's based out of MATLAB, so there are some syntax overlaps between MATLAB and Matplotlib as well. But there is a more Pythonic way to do. I come from a MATLAB background, so I kind of use that MATLAB syntax as well. So I'm going to show you guys today a little bit of both. But we won't get into the nitty-gritty details of how it is. This is to give you an exposure of how you can use it and what kind of facilities or features that are available with Matplotlib and Seaborn. So before we do that, we want to make sure that you guys have installed Matplotlib. If you are using conda install, this is the command to go with. Otherwise, pip install Matplotlib. And once you do that in Jupyter, if you're using Google Colab, you should be good to go right away. You just start with import matplotlib.pyplot as PLT. PLT is the usual name you would see for the shortcut for using Matplotlib library. And to make sure that in Jupyter, the plots come inline, so you want to add this line as well, which is matplotlib inline. And this command is only used for Jupyter notebooks. If you're using another editor, I use Spider a lot. So you'll be, if you're using Matplotlib in Spider, then you'll be using plt.show, which essentially will show your plots in a new window as a pop-up. That's something you will want to know. We'll walk through a basic example on Matplotlib. Most of the Matplotlib tutorial that I put together here is based on Numpy arrays because it is being used. It is very good at manipulating matrices, and Seaborn, on the other hand, is very good at manipulating data frames in a pandas data frame, which you guys saw last time with Yogita. So we'll go over that when we get to Seaborn. So here we start with a Numpy array. I'm just creating a simple Numpy array from 0 to 5, 21 values. There are some people use linspace, some people use arange, both gives the same output. And then I'm squaring that particular array. So here is how the value of x vector is, and this is the value of y vector. So we'll start with the most basic matplotlib command, which is just plotting that x array with the y array, or x vector versus the y vector in a red color. So the syntax goes like this: plt, which is a shorthand for matplotlib, and we are plotting it. And what goes on your x-axis is essentially your first argument, and then y-axis. And then if you want a particular color line, then you say what the color is, red. And if you want to give your labels, then you just use x label and give your actual axis name in quotes, and that will fix your axis as my x-axis. And your y label, and then we have the string title, and then we need to have plot.show, so it actually shows the plot. So this is a very simple, quick line plot that you can create with Matplotlib. Now, like I said, Matplot is very versatile. So you mostly in scientific papers, you have space issues, so you want to use the full canvas to as much extent as possible. So there's a concept of subplot, which is essentially you can imagine like you have a paper, and then that paper is essentially divided into 2 or 3 or 4 grids, and then each grid has a plot that you want to show. So that's the same concept this is built upon. It's called subplot actually. So plt.subplot 1, 2, 1. What it means is 1 is the number of rows, 2 is the number of columns, and you are going to be plotting number 1. What should go in the first plot? You want to say that. And then you say plt.plot x and y, you're plotting the same array. I'm just plotting the same array, and I'm saying I'm going to give it in blue, and I'm going to use a pattern of dash dash. And this is something that comes from the MATLAB syntax. In MATLAB syntax, this is how you would do when you want to plot it. And the same thing works here in Matplotlib as well. And then again, we say that this is the first row, second row, and you want the second plot to be plotted y versus x with a red star and a dash. And that's what it's doing exactly. So it implicitly actually defines the figure size, a fixed figure size, and divides it into 2 plots. And the first plot, you start with this one, and the second plot, you start with this one. However you want to, you can manipulate it, but this is a very simple plot of how you would do if you want to have 1 row, 2 columns, 2 plots. And here is a same example with 2 rows, 1 column, top and bottom, a slight manipulation of the data. So plot B minus minus means blue dash dash line. Red star dash means it's again a line with a star in between for each data point. And Matplotlib is Python, as you all know, is very object oriented. So Matplotlib follows the same idea. So, and these are some very simple basic plots that we have so far seen in Matplotlib. And now we are going to break that down to inculcate the little bit of object oriented class and objects that we want to use in a more Pythonic way. That's where this comes in. So the main idea for an object-oriented method is to create the objects. And in this case, because it's primarily a visualization library, so we create the objects for the figure that we are going to develop, and then call that object and attribute properties to that object. So we get the level of customization that we want to. So let's take a look at this code essentially. So here I'm saying fig is equal to plt.figure. I could have just written this. That would just mean it's going to instantiate intrinsically. Here we are creating an object explicitly. So whenever I want to call the figure, I just call fig dot something. And then I am going to that object, I am adding the axis, I'm adding the axis, and here these essentially is the left, bottom, width, and height. You can change this. Most of these quantities are in fractions. You can change to however the field that you want to place it here. And then once you have an object for the added axis, which is the axis here, and then on the axis, you're going to say you're going to be plotting the X and Y. 2D, we are still talking about 2D. And we are saying we want a blue line. And then to the axis, we are setting our X label, Y label, and the title. It is very similar to what we saw before. It's just we are doing in a more Pythonic way, which is the object-oriented way. And this is really good because this gives you a lot of commands that you can use for customization, which we'll see a little bit below. So right now it is getting a little bit complicated, meaning first one was first basic plots that we saw were very easy. And this one is a little bit more complicated where we are trying to create this plot where you have a big plot and another subplot within that, let's say focusing on specific area. That's a common thing you would want to do in the engineering field, where showing like a mechanical stress strain curve and focusing on a specific part to zoom in kind of thing or a zoom out kind of thing. And that is useful in the financial domain as well. So we'll look at how to do that in with a very simple Numpy Array example. So again, we start with a blank canvas and we create the object fig. And then to the fig, we are going to add two axes because there are two plots. We add one big axis and the other one is with respect to these numbers. So this one starts at 0.1. This one should be a little bit offset from that. So that's how I decide. And this is 0.5 because it's going to be halfway up from this one. And that's why we have 0.5 here. And this is just the width and the height of how big the plot you want to be. And then that would essentially create your larger figure and the smaller figure, which you have here. So we have one figure object, but we have two axes. And then on the axis, you're going to say, okay, we want to plot this data. And we are going to set the labels and titles for each plot separately. And that's how the customization essentially for Matplotlib will work. This is again a little bit more basic, trying to create two objects with the plt.subplots, fig and axis. And then we are using those objects essentially to create our plot here. And then moving on to, this is just to show you guys that if we don't give any data essentially like this, then it's just going to plot two blank plots with a specific dimension, with the default dimensions that Matplotlib does, which is 0 to 1 essentially. Because it's two rows, one row and two columns, it's going to divide the space, and the x-axis essentially looks smaller than the y-axis. And when you just type axis, because this is an object, you can see that the data type is object. I just wanted to show you guys that these two are object types, and I'm showing you that here. Now that you have two objects, you can it's a very Pythonic way to just iterate through the objects, right? So it's like if you have a loop, you just iterate through them. So it's just like that. So you can iterate through them, and then within these two plots that you have created an empty plots here, you can iterate through them axis, and then in each axis, what are you going to plot? That's what you are going to give in here. So it does it in just in a for loop, how you would do it. This is another way to do the same thing, which we did a little while back. So the one disadvantage of doing such subplots, if you see here, there's a slight overlap. Matplotlib by default doesn't take care of it. So the Y essentially should have come here, or there should have been more space, something like that. So in MATLAB, this would be a difficult thing to fix. You have to manually set the size to and try a couple of iterations to figure out what the size. Matplotlib actually gives a very easy way to fix that issue. You can just use fig.titleLayout, or if you're using plt.titleLayout, and it actually fixes it. Avoids that overlay between those two plots, which are side to side together. And that essentially pretty much completes the customization for at this level to that can be attained with Matplotlib. So I wanted to see if you had any questions so far, or did I go too fast? Anything we want to discuss at this time? Otherwise, we'll move on. Okay. Did anyone have any questions?
I think Aziz just unmuted himself.
I mean, it's been good. It's been good. We're following.
Sounds good. It probably takes a little time to get used to that syntax if you have not used Matplotlib before, but otherwise it's a pretty simple syntax compared to Matplotlib. To get the same plot in MATLAB, you would have to write a lot of lines compared to Matplotlib. So that's why I think I like Matplotlib rather than MATLAB. Anyway, so the next thing that we want to see from a level of customization is the figure size, the size of the figure, the aspect ratio, the length, the width and the height ratio, and the dots per inch. How clear do you want the picture to be, and how to save the picture essentially. So the ultimate purpose is not to just create notebook. If you want to present it to the leadership team, you want to be able to present that. There's a third library called Plotly, which essentially lets you do an interactive dashboard kind of thing. If you're using Matplotlib, that gives you a way to for leadership team essentially who wants to just look at pictures, and it's a easy thing to do using Matplotlib. So that level of customization is what we'll go through in the next couple of minutes. So like I say, DPI is dots per inch, how many pixels per inch, and the figure size is essentially your length versus width. So now, as you have seen so far, all the plots are pretty much the same width and the height. I haven't changed anything before. So now I'm going to say the figure size should be 8x4, which is essentially here 800 by 400. That's what it changes intrinsically into. And this is because of the dot per inch that I'm giving us 100. So if I give 1000, then it's going to change to 1000. And depending on how clear you want the picture to be when you download it and zoom in, you will set this dots per inch criteria. But the 8,4 is essentially this width and the height. That's what I'm setting here. Now that I've said this, I am going to run this part of the code, which essentially is using the same Numpy array and setting the titles x-axis, y-axis, but I am overwriting and saying the figure size of the subplot should be 12 versus 3, and that's what we are doing here. Now, as you can see, there are some plots where you want to have more width versus more height. So you change this accordingly. And in a Jupyter notebook, it will not make much difference. But when you download that picture, it will make a difference as to how your size looks like. Because the default size doesn't quite work well when you export the save the pictures essentially. So that the next step is essentially to learn how to save the figures. To save the figures, all you got to do is the object that was created here. You just say object.savefig and give a file name .png. In case of Jupyter Notebook, what's going to happen is you see this folder. This is where your picture is going to get saved. And from here, you can actually download and save it to the necessary folder. If you are using like a spider or something else, then you can actually give the whole path in your local machine where you want to save it. It will just go inside the quotes and it will save it right away there. And you can run this through a loop if you have a series of pictures that you want to save, like a gradient descent or something. If you're working on a gradient descent algorithm, and you want to show how the optimization is happening, that's an easy thing to do with a picture series of picture. And you can also customize to saying, okay, you just want every 5 pictures, save the 5th picture. That's possible too. As we saw before, we just use a for loop and iterate through that and just have the save picture only when it reaches a particular number. It's a simple for loop concept again. Because Matplotlib is very Pythonic in nature, all the usual commands that works in Python also works with Matplotlib, and that is a great thing. And this particular save figure, essentially what it means that you can specify what the output format is. There are other output formats as well. The other ones are JPEG, EPS, SVG, or even a PDF. Actually, you can save it through that. I usually tend to do PNG or JPEG and then put it together myself on the PDF. But there are people who know exactly what they want and they directly export it as PDF. Here, we are just giving a dots per inch, which is 200. And we are allowing it to save the picture as a PNG file, which is very cool because when you see the difference between this picture and this picture, one is much more clearer, even if you zoom the picture after you download it. And that's the advantage of giving a specification of how many dots per inch do you actually want to see. Moving on to the next section. This is some level of customizations that I wanted to show, essentially beyond the axis, beyond the title. The other thing you would want to show is the legend. So and you can actually set the title, a fixed title or a fixed set of labels, and then we run the command. We are still using the same Numpy array, just the X part of it. We are not using the Y anymore. Instead, I'm using X square and X cube, and I'm showing 2 different lines on the same plot with a legend, essentially, which one corresponds to which one. And the legend, all you have to do is ax.legend. It has further options as well, which we will look at here. The additional optional argument for legend essentially allows us to place the legend in a particular way. So the basic options are location should be 1, 2, 3, 4. 1, if you think about it, it's the upper right corner, and then 2 is upper left corner, 3 is lower left corner, and then lower right corner. So it's more like this. So kind of easy to remember because it comes in an order, at least for me. So as long as you give which location you want it, it will place it in that particular area, the legend. If you don't give any location, if you want Matplotlib itself to choose, then you give location 0, and the default location it chooses is here. So if in this case, location 0 actually works because that's what we want, upper left corner. So if I give location is equal to 1, it's gonna go there. So that gives you a set of level of customization on where the legend should be set. There are ways in Matplotlib to set the legend such that it doesn't overlap plots. That's a little bit more advanced, but you will figure it out eventually once you know these are the objects that you need to be using to customize your figure. And then the other options is, like I said before, it's more in a MATLAB style to figure out how the width of the line is, how the color of the line looks. This is a simple one, just like the ones we saw before, where we are using a green line and then a blue line, but it's a dotted line instead of a star. And then you can try different color parameters, and these are just showing you the color parameters doesn't necessarily have to be like B for blue. So that's something you have to remember, right? So the other way to go about is just spell it out, blue. And then this particular parameter, what it does, it makes your line a little bit transparent. It goes from 0 to 1. So this is essentially setting it half transparent. And if you are more familiar with hexadecimal colors, I'm not, but I wanted to show you guys that this is also a way to go about it. If you have worked with Tableau a lot, you probably will be much more familiar with these hexadecimal color formats rather than actually just giving blue. Because when you want a more specific nuanced color, you just find the hexadecimal color and even just Google the hexadecimal color. And if you pass that as an argument, it's gonna take that as an argument and plot your colors. The other level of customization is essentially here, which gives you, just to give you a sense of what level of customization on the lines can you do. And all this will be useful when you decide, okay, this is how I want the plot to be, and this is the part that I want to highlight. So if you look at these plots, the first one is using some kind of line width. So the width of the line is very small compared to something like this green or this blue. And then that particular argument is called line width, where you're setting what the line width should be, 1 versus 3. And the line style, LS is for the line style. What kind of style do you want? Do you want a square with a particular color inside, or a different marker like a circle, or just a dot and a dash? So these are some markers, but there are a lot more options than these. And then what is the size of that marker? So each point on this plot is customizable. And that's what I wanted to show you a demo of here. The final line here, that pretty much uses most of it that you would want on a daily basis, which is essentially showing you're plotting a line X and the values of X with the X plus 16. That's just to show you the difference between the different lines. And I'm using a purple color with line width as 1 and the line style essentially dash. And I'm using a marker, yes stands for square, which is what we are using here. And the marker size should be 8. So you can actually see it pretty good. And the marker face color, which is yellow, which is the filling for that particular marker inside that square. And then the marker edge width, how thick do you want that square to be? And that's what is specified by marker edge width and the color. So there are different levels of customization for each data point. How do you want to highlight that point? That's what I'm trying to show here. And this gives you a pretty good control of how the plot wants to be. This level of control is easy with Matplotlib, and in Seaborn, same plot is possible, but it just uses a default value setting for most of this. And that Seaborn is more for exploration library, and this I would say is more for customization to show to somebody the particular picture, the particular analysis that you have done. So it looks so beautiful. And the last section I want to wrap up for Matplotlib is to give you the control for the axis. So essentially what we are trying to do here is sometimes it's possible that the plots are of different levels, meaning this ranges from 0 to 5, while the other ranges from something else, 2 to 5 in this case. I'm just focusing on this particular thing. So that's possible as well. All you have to do is create those two objects, and then iterate through the objects. So axis 0 means we are talking about the first plot. Because we are using Python, it's going to iterate from 0 to the number. So axis 1 refers to the second plot, and the axis, the third element on the axis essentially refers to the third plot. And you can customize each of them in combination with these, and that would give you like a really beautiful plot. And just say figure has to be tight. So figure layout needs to be tight, so there is no overlap when you have those axes and the titles. And that's how you control what you are showing in each of the plots. There are also some special plot types within Matplotlib, other than line plots. So we have a scatter plot, and this is a very simple scatter plot, again using the same X and Y. And then here to demonstrate how a histogram essentially will look, I am importing a sample from 1 to 1000 and then taking 100 elements from that array, and I'm plotting the histogram. This is to show you that there are other special plots possible, very much possible with Matplotlib. We have just scratched the surface at this time. And the well-known box plot. Box plot is much easier in Seaborn. When we look at that, we'll see that. But in box plot, in Matplotlib, what you can do is this level of customization. If you see in Seaborn, they are all going to be black, but you see in Matplotlib, you have a level of customization that can be done within the box plot, and that's why you would use this versus the Seaborn box plot. The other types of 2D plot styles, you can also do 3D plot styles. I'm not going to go too much into the 3D plot styles, but I'm going to show you a quick overview of what other 2D plots are possible. So this is a scatter plot, and this is a step plot where it is just increasing the steps each time the X value increases, and then bar. And if you have two lines, you can actually fill them, just like in Tableau, you have that area plot. So this is possible as well. And here is a demo for the 3D plots. 3D plots actually are really cool and used a lot when you are working with just matrices. A lot of machine learning algorithm intrinsically uses matrix calculations, right? So if you want to visualize some of those, not probably real world problems, but to understand how a rotation matrix works, then your 3D plots are a good source of that. To run the 3D plot, essentially I am inputting two other libraries. One is from the 3D axis, and this is just for the data purpose. I'm importing from the scipy.stats, a multivariate normal distribution. So so here I am creating a mesh grid. This is to demonstrate so 3D plots essentially means you have 3 axes, right? So you need to figure out how your x-axis, how your y-axis, and how your z-axis are going to look in a 3D matrix. What do those numbers represent, and how do you want it to be plotted? So you would create what is called a mesh grid, and I'm using Numpy to create this grid. When I say grid, this whole thing is what I mean. What is my start point, what is my end point, and what is my height going to be? That is exactly what I'm defining here. And then I am creating some empty arrays and empty matrices, and I am iterating through it, and I'm filling that particular matrix with values from a normal distribution. This is how a normal distribution would look like, but we are looking at it in a 3D format. The simplest would be to just have a wireframe, but you can also color the matrix. Because it's a normal distribution, we know already that the center is going to be the highest in density. And that's exactly what this legend is showing. The way to do that is to do the color map here, which comes from the Matplotlib, called CMap is the object that you want to use to do the color mapping to the wireframe. So if you just wanted a wireframe, so this would be a blank wireframe. It will not have it will just show you a blank normal distribution, which is essentially what we created in this loop as x, y, z, and we are just passing that along. So depending on how good you want your 3D plot to look like, you go one way or the other. This is part of your assignment, essentially, which comes as try it at home. So the assignment for Matplotlib that I would like you guys to try is to figure out how this particular function is going to be manipulated to understand how a rotation matrix works and rotate the 3D picture. And another quick demo of how in a real life how you would be using. So you have a function called flex qubit. This is from more from the engineering domain. You have a function which is 3D and it uses cosine function and iterates through the degrees and creates two bumps essentially. So this is how essentially this function would be. If you look at just the numbers, you wouldn't see it, but in a 3D plot, this just looks really cool when you plot it in the 3D plot. And I'm using the subplot that we saw before, essentially trying to show you guys both the filled wireframe. The one that I showed you, demoed you here, was unfilled wireframe. Here, each of the squares are actually filled. And then this one essentially shows you also where the highest density is. So this is more, this is what I was talking about when I was telling that you can see how your gradient looks like. If you're using a gradient descent, for example, and you know your function for your gradient descent, so you iterate through those values and then figure out how your gradient is and where it is kind of settling, where your final solution is going to be. And that's pretty much all I had for Matplotlib. So some of the other things that I thought you should be aware of is Matplotlib can create animations. It can create contour plots, which is also again used a lot in engineering when you look at the surface and convert it into a 2D image. And they also actually have 3D contour plots. And if you work a lot with just images, I am sure that again comes from Matplotlib. This is a MATLAB command actually. I am sure can be used to visualize the images, more like X-ray images, that kind of thing. If you're doing image processing in Matplotlib, then you will be using those kind of plots a lot more than the tabular data plots like this. So this is the last part, is just the assignment, which is essentially asking you to modify this particular code and look at how the rotation matrix is going to change. And we have some hints here, and have at it whenever you can. I pretty much have the solutions here. All you got to do is rotate the angle. So essentially, if I say 60 here, it's going to have a rotated angle a little bit. So I want you guys to try out and have an idea as to how these rotation matrices work. And that gives you that also gives you an idea of what happens when these rotation matrices are multiplied in case of most machine learning algorithms to an actual matrix. That's pretty much it for the Matplotlib. Any questions before we move on to the Seaborn library? I know that was a lot to take, so have at it slowly. I pay for everything.
Yeah, Nisha, you nailed it. What you just did now, I can't even try. I can't even try it. Running through what you just ran through in less than an hour.
Yeah, I think Matplotlib is a little bit more nuanced. Seaborn is going to be easier lecture, so this is the one to go with. But I wanted to show you guys what is possible with Matplotlib, and you have the notebook, so have at it.
Yeah, so Nisha,
All
this
right.
is what we're going to do. As soon as we're done with Seaborn, maybe we should just take in tabular data and use Matplotlib to just show how that works. Because so far we have just been using Numpy to generate the figures, and I know some people are like me. They're not very comfortable with Numpy arrays and code generating figures like that. I would rather, because of my background in accounting, I would rather work with figures, not a spreadsheet person. So I like seeing tables, so I would rather not see Numpy the arrays. That's for me, but I know some other people are comfortable with that. So in order to help people like me,
So Seaborn, I'm actually going to be using real data. So essentially the pandas data that Yogita was showing in her last lecture. So this is going to be a little bit more on the lighter side. But towards the end, there are complicated plots that you can do with Seaborn as well. So that's only a small section of the lecture today. So we'll just spend a little bit of time on that. But most of what you do in a day-to-day exploration, that would be your Seaborn library, not essentially Matplotlib. And this is what I would recommend as well if you're just starting with visualization libraries. So, like I said, Seaborn is actually built on top of Matplotlib, and it's much more flexible with pandas. Essentially, it's essentially built for pandas data frame to handle pandas. It can handle Numpy as well, but most people use Seaborn with the pandas data frame to visualize their data essentially. So in our case, if we once we do the installation, again, it's the same thing. It will be either pip install Seaborn or the conda install Seaborn. And Seaborn, just like Matplotlib, is going to have both 2D and 3D figures. It can be used for scientific purposes as well. It's a little bit more nuanced to control the axis and the figure objects. I would use Matplotlib for those purposes, but Seaborn is still an option for that. So if you're working essentially with the data frame, this is the one to go with for sure. Okay, so to start with, I am also importing Matplotlib here as PLT, and Seaborn is usually imported as SNS. Just because I have some arrays and matrices coming up, I'm also importing Numpy, but we are going to be using pandas data frame as for the most part of Seaborn demo today. So pandas, I'm importing as PD, Numpy as NP. Those are all pretty much standard. You can actually do anything you want, but this is the Pythonic standard that most people use. So the problem overview is pretty much the same data set that we saw from last time that Yogita had, which was an insurance data set, which has about 7 or 8 variables. One variable is called charges, which is essentially your continuous variable. These are categorical variables. Smoker, children. Children is it's still an integer, but it is indicating in a way a categorical. BMI is continuous, age is continuous, and sex is again categorical. I'm just going over the type of the variables because the way I have put together this particular notebook is based on the type of the variables and the plots that you would be using for these variables. So the first set of plots that we are going to see is the distribution plots. There are many options to do these distribution plots for using the Seaborn library. We have the dist plot, joint, pair plot, rug plot, KDE plot. We'll take a quick look at all of these. But with the particular data. So what I'm going to do is start importing. The data is already there it's publicly available. You just have to run this notebook and you should be able to see the data. And this is how the data essentially looks like. So we have 7 variables, like I said. BMI and charges are the continuous variable which varies throughout it. Age is more integer, children is again more integer, sex, smoker, region, they are all categorical variables here. And this is like a perfect data set. So it doesn't have imputation going on or anything like that that we need to do at this time. The focus of this particular notebook is on the visualization rather than the imputation techniques that we would probably be doing with pandas. So I'm going to jump right ahead into the visualization. So the first visualization that we want to do is look at the distribution of certain variables. So like I said, BMI and charges are the continuous variables, and this is an insurance data set. So each record essentially means that this particular female is of age 90, has a BMI of 27.9, has no children, and is a smoker and lives in the Southwest region and encountered a charge of $16,884.924 for her medical conditions. That's essentially what this data, each record in the data set means. So we are looking at the distribution of charges. And like I said, this is a perfect data set. So we don't have any negative values or anything like that. And you can see that most of the values fall on the positive range, which is a good thing. And most people fall around between 0 to 20,000. There are some here. And that's what you would want to infer from this plot from the Seaborn library. Next is to add the kernel density estimate, which is essentially giving you the distribution of how this looks like. This is a more broken out histogram, and here I'm lumping a couple of them together and having giving a bigger bin size to essentially see how the distribution looks like and also see the KDE. And you can imagine as to how the distribution would look like just from the histogram. One thing I would say, when you set the bin size like this, bins equal to 10 means I want 10 bins for the whole data. Be aware of how you set the bin size, because depending on how you set the bin size, the histogram is going to look different and the KDE is going to look different. In this case, it doesn't really quite matter, but there are cases in real life data where this actually matters. So you need to be careful about how you're testing, how you're visualizing your histograms with your number of bins and the bin size. The next one would be the joint plot. So there are many different options. I'm going to go over a few and then move on to the next set of plots. So these are the options that you have for a joint plot. Joint plot essentially helps you do a univariate or a bivariate plot. In this case, I'm going to see how the age is distributed among the charges, if there are any patterns for it. So as you can see, between 20 to 60, there is a cluster here, and then there is a cluster here, and then there's a cluster here. What this essentially means is that between the charges of 0 to 10,000, the range of the age varies all over, and there is a steady kind of increase between this age group. And same happens between 10,000 to 20,000. That's the same format. As the age increases, there's a steady increase. But then it has its own cluster between 30 to 40, again, the 30 to 60, I would say. And some of them are much more different than the others. Those are probably outliers, but that would be the interpretation you would get from this particular joint plot of just a numeric age variable, integer in this case, and a continuous variable such as charges. So I am doing a scatter plot, which is the first option here. You can also do a reg, which is essentially regression. It would plot a line. For this plot, it would not be appropriate because this is looking much more different than a regression. But those are your other options. One other option I want to show for the kind is the hexagon. So what this does is it groups some of these points, and forms a hexagon. So the darker the color, that means there are more points that are lumped in together. The lighter the color, there are very less points in those areas. That is the kind of information that you're getting. This is a natural way for upper leadership kind of people to essentially not be distracted by so many points and just look at, once you show this plot to anybody, what they are going to see is, why are these darker and why are these light? That's the first question they're going to ask. And that's the kind of information you would want to show if you want to highlight that, okay, this particular part is dense compared to other one, then you would be going for these kind of plots. And which is what we are using in this data set. The thing that I wanted to highlight here was these particular between 10,000 or between close to 10,000 and 0, these are the particular ages that are of higher density, even though there's a fixed pattern that we saw from here between 0 to 10,000, 10,000 to 2,000. That's the information I want to get across from this.
Nisha, I think there's a question from Amir. It says that you should please elaborate more on the visualization of hex.
Sorry, can you repeat that again?
The question is in the chat. Please elaborate more on the visualization of hex.
Oh, please elaborate more on the visualization of hex. Okay. So hex, what it does is it's the same as scatter plot, but it's grouping some of the points and showing if there is a higher density within a particular area. So this particular hexagon is much more darker than something like this. What it means is that there are no points in here, but there is a high density of points within this area. So between somewhere around 26 to 27, and between the charges, this is probably about 5,000, right? So 5,000 to 6,000, there is a lot more number of records of people that fall in this category. That's what it would mean. So that's the difference that you would, that's the insight that you would probably get from a hex plot versus a join plot. Join plot is looking at it both at the same time, right? And in the hex plot, if you want to drill in and see which particular subdomain is, or sub BMI and sub charges in this case, is much more dense than others, that's what you would see. You would not be able to see that from just a histogram of BMI or just a histogram from charges. Looking at it together and at the same time, how dense it is, that's the information you would want to convey to your stakeholder with this kind of plot. And this is something, it would be very obvious when you use a hex plot because of the way how it plots. Looking at the density in each hexagon. You can actually change the hexagon size and stuff, but this is the basic hexagon hexagon join plot that you would get just from using this one line. Hope that makes sense. Okay. The next one would be to, so like I said, there are many other options as well. You should try them all if you can, whenever you can. But these two are the ones I use a lot, and that's why I'm just demonstrating just these two. Moving on to the pair plot. So pair plot, as it says, essentially does a pairwise comparison of any two variables in your data frame. And you can actually do a pair plot for the complete data frame. Any set of continuous variable will be done as a pair plot. One thing you should probably be aware of, it will take a larger very lot of time if it is a larger data frame. Here we are okay because it's a very small data set that we are working with. So be aware of that and don't use it blindly. And we also have lesser variables here, and it is easy to do a pair plot between the variables and make some inference in there. So this is exactly what we saw as a scatter plot, which is also being shown as the pair plot essentially. Pair plot essentially shows all the pairs possible for the continuous variables. So BMI, children changes, no categorical variables will be plotted in here. So one inference that we could make again is the age and charges distribution. And if you look at the BMI and the age, it's all over the place. So we know that there is not really much going on between BMI and age. There is no correlation. That's something you could infer from the pair plot essentially. And that's how you would, the diagonal essentially is the histogram plot for each of the variable themselves. And our BMI is actually perfectly normally distributed if you see it. And this is our age distribution. So most are in your smaller age category, and there are this reasonable distribution between the age category of 40 and above as well. So one thing that tells me right away is that if you're looking at age around 15 to 30, then you would want to drill down a little bit deeper as well, because there's a higher count in this particular bar compared to the others. So you don't want to get a wrong impression about that. So the other option is that the same plot, you can use the categorical variables to see how do they differ based on those categorical variables. So in this case, I'm using sex. Sex was one of the variable that we had in the data. So based on sex, male, female, I am going to be looking at how do they differ, if there is any difference between the males and females across each pair of the continuous variables. So when we do hue equal to sex, it's going to differentiate between the male and female, and it gives more like a kernel density estimation rather than the histogram plot like here. That's the difference you would see between a pair plot using a categorical variable versus a pair plot using just the whole data set. And here, if you see everywhere, pretty much the males and females is distributed all over, and they do not seem to be different, except maybe in this area where the charges are slightly higher for male beyond certain level, say 30,000 or something. There's a slight difference, but this could be because just that we don't have much data beyond at the higher. That's where this plot essentially comes in. If we see there are less data points here, so that inference that you make that males are probably being charged a little higher than females might not necessarily be valid. So that's something you want to take into account when you interpret the pair plot. What's the distribution? How many people, how many records do we have in that area? And that's a mistake I've seen many people commonly make when they interpret the kernel density estimate plots, such as this one. But other than that, the males and females, I would say, is pretty much the same across age. They have a same distribution. They have the same distribution for BMI as well. Both look pretty normal. And the number of children that we have to say that 0 children, that's equal distribution. 1 child, there is probably a slightly higher distribution for males than the females. And 2, again, pretty much the same. 3, pretty much the same. 4, again, pretty much the same. And 5, we actually have very less data points in this data frame. Some other useful plots are the rug plots and KDE plots. These are not very commonly used, but I like to use it sometimes, mainly when I want to see exactly as to where the data points lie. The KDE, like I said, just from the interpretation of this, could be a little fuzzy because it approximates a distribution on the data point, right? So in this case, we exactly know that actually there are no data points here. Even though it goes beyond 0, we know that there are no data points here because these rugs are actually marked only from here. And the more the rugs, you will see much more denser. And the lesser the data points, you will see just one stem coming from the bottom floor of this particular grid. And that's the main use for this, to kind of help interpret the KDE, because it kind of draws a normal distribution around each point and then averages it over the whole data set. And we want to be careful about that when we use it. So the rug plot essentially here is the orange one, and the KDE plot is the blue one. So I'm plotting both together. So the rug plot, what it does is it marks each data point, each data point as a dash in a univariate style, meaning, so I have a data point right about here, which is 500 or something, and I know I only have one data point around 63,000, and this is around 62. So that's what is the information that is conveyed by the rug plot. Does that make sense, Amir? No, it's not the number of data points. If you have more than one data point, you will see a double line here, essentially, and it'll be on top of it if it's the exact same. If it is not the exact same, you would see on the side. On each data point, it's gonna draw a stem. So what this means is that there is a very close distribution between each data point here. And it's quite possible that there are multiple data points just around this mark, like say 10,000, for example. That's what it would mean. Yes, it does not show magnitude. It just plots the data point on the scale. If you are plotting just the charges in a picture, then that's what this does essentially. And this is to make sure that we understand the KDE plot. Just from the KDE plot, you would think there are some data points here, which is not true. And that's why we want to see the rug plot as well. So we make sure we understand that the actual values for the charges only start after 0, and there is actually nothing in the range of minus 10,000 to 0. That's the message, essentially, to combine the KDE and rug plot together. Okay, moving on to the categorical plots. There are a lot of categorical data plots for the Seaborn library. The basic, we'll just go over the basic ones and the beautiful looking ones. So the basic ones essentially are the bar plot and the count plot. So the ones that we want to go over for the bar plot is that it does have a default estimator, which means the default estimator is that it shows the average of means. Here I'm using the charges, and I'm asking it to divide it by sex. And within each sex, what's the default estimator would be the mean. And if you look at just the SNS bar plot, we would think that, okay, the male is a little bit higher compared to female. And then we would want to also see how does the median overall look across all the females and the males. And that's what this says. And if you look at the median, it is pretty much the charges are pretty much actually the same. There are other estimators as well that you can use, like standard deviation and others, depending on your needs. But the simple bar plot by default uses the mean as an estimator and shows you how it is distributed between the two values of the categorical variable, which is sex in here. Count plot is very similar and is related to the bar plot, but it shows the raw count as to how many, so within the female, what is the count of data that you have for the female versus male. So that again, you can see is kind of pretty similar. So there's an equal distribution of records between the female and the male. So we want to be careful as to whether we are using count plot versus bar plot, which actually shows you the range of the values here, while it just shows you the count of the number of records between the two categorical values of sex. Here comes some of those beautiful plots. which is essentially our box plot and violin plot. So here I've used a different categorical variable. I'm using region. We have 3 categorical variables, and we have used sex so far. So now I'm going to see the distribution within each region. What is the insurance charge distribution? And we are using a rainbow palette to see that distribution across the box plot. And I am also setting the Matplotlib plot figure size to slightly bigger, so it looks more cleaner. So as you can see, this box plot essentially follows the Tukey fences. So the lowermost is the lowermost value that you would find in this region. And this is the first quartile. This is the median or the second quartile. And the third upper bar is the third quartile. And then this is the third quartile plus the interquartile range. And anything outside this is just plotted as dots, meaning they are outliers based on the intrinsic box plot thresholds based on Tukey fences. I hope that is clear. If you do not know what Tukey fences are, I would suggest looking it up, as that's an important part to kind of infer from these box plots. The other thing is we can actually swap the box plot, meaning we can make it horizontal like this, and we can also actually do the entire data frame. Here we don't have much variation in age. We do have much variation in age. The reason it doesn't show up is because of the scale of the charges. It's much bigger than age, BMI, or children. But this is this plot is more to demo that you can swap it and make it horizontal. And that's the idea of this plot. And you have other options as well. You can compare a male and female within each region and use a different color palette to set across the male and female. And that's an example here that we show with the box plot. Box plot is often also called like a whisker plot because these look like whiskers. And that's a common language people use for both as a box plot or a whisker plot. It essentially shows any kind of quantitative data and the relation between them across a categorical variable. That's the main reason you would want to use a box plot. The other plot I like is the violin plot, which is very similar to the box plot, except it uses a kernel density estimation and the rug plot that we saw back here, which is essentially this plot, but in a way that it looks like a violin, and it's called a violin plot. I am plotting again the same data that I did for the box plot, and I'm plotting across the sex, the categorical variables. How does the female and male look? We already saw that there is not much difference, which is the same thing that this violin plot conveys as well. And we can also, I'm doing the same plot across region, just like I did with the box plot. But again, within the region, I'm showing how does it vary between female and male. So we are using 2 categorical variables and the continuous variable. So we are bringing 3 dimensions into picture. And this is a little bit more nuanced to interpret. So the other way to go about the same plot is to just show the female over on the left side and male over on the right side, because this essentially is a duplicate of this kernel density is the same as this one. So if you are really looking for just the female and male, how do these kernels differ? Then all we have to do is show half of the violin plot from this and half of the violin plot from this. And that's what this does. The command to do that would be split equal to true. So it just splits this into half and splits this into half and merges them together. And this gives you the same interpretation. Within each region, do the males and the females look alike in distribution? If you see, there are some slight differences at the far end towards the higher charges, but then again, we have to remember that there were not many people in this higher charges from our rug plot before. So most of our records are in this region, which is 0 to 20,000, and you can see those rug plots. The rug plots, if you use a different color, you would be able to focus on them here. And the other two plots is the strip and swarm plot. Those are pretty simple, pretty much the same as the rug plot, only it looks beautiful, like a butterfly kind of thing, and it doesn't add any extra information as the violin or the box plot. It just plots the data point as to how dense it is within this region in the 10,000 to 20,000 area, and that's the kind of inference you want to get from these plots. And lastly, we could combine these categorical plots. So here what I've done is combining the swarm plot with the violin plot, and this is kind of giving the combining the violin plot with the rug plot, which is the default. I'm just combining the swarm plot with the violin plot to show also how many data points at this particular value of charges. I'm plotting BMI here. So at this particular BMI, what does the density of my records look like? And so let's see, for Northeast, we have a lot more people, around 34 or 33 BMI compared to right about 30. And that you would not see just from the violin plot, but you can from the swarm plot because of the way the number of records is displayed. That it doesn't add any particular information to it, then you would do it separately. It just looks beautiful. So many people use it when they present to the business leaders, analysts, or product managers. So lots of choices there to combine different things, and you can come up with beautiful violin plots, box plots. And that pretty much ends most of the Seaborn basic concepts. The last two things that I want to say is the matrix plot, which essentially shows you the correlation between the variables in a way. The easiest way to go about it in this particular data set is to see if there are correlation. How is age correlated with your other continuous variables? In this case, age, BMI, children charges, they're all continuous variables. And we are looking at the correlation between them. And as you can see, this is a demonstration of just the visualization, and nothing is actually greatly correlated in this data set. To actually demonstrate how you would create a heat map in an actual data set, I'm downloading one more data set here, which is the flights, and I'm converting it into, this is something you would have seen in the NumPys or Pandas presentation, and across each month, what did the number of flights look like? So here, this is a good one to make an inference essentially with a heat map. So when I plot with a heat map, and I'm using a color map of cool warm with some gap between the colors, you can easily see that in 1960, July and August were the months that had the highest number of flights, meaning the red is about 600. And it has kind of consistently increased over the years from 1949 to 1960. The data set is pretty simple. We are just using the month and the number of flights in each year of that month. So this is a good way to show how the flight pattern has increased between the years 49 to 60 over the years. And within each year, how did it look like? So each year, if you see, the summer season has been the kind of the highest, the rest of them are in the lowest. And in this, again, higher than the past years, but within that year, again, summer is the highest. That's the information you can glean from such maps. One more possible seaborn map is the cluster map. So here I'm still using the same flight data. I am looking at how many flights for each month within each year, and then see how we can cluster it. So if you look at this particular plot, it is not anymore in order of the years like this one. And it clearly shows that in all the years, July and August were the months that had the highest number of flights. I also normalized the number of flights to a standard scale of 0 to 1. So the increase in the number of flights does not affect the plot. And that's when you see the clear pattern of, okay, in summer is when the highest number of flights have always been across the years. But to glean as to which year had the highest, this plot would probably be better. And that's why cluster map comes into picture, to figure out if you're not worried about the time pattern, that kind of thing, and you're just looking at a specific pattern across the whole data set, this is much more useful than a correlation plot or the heat map plot like this one. I think that's pretty much all I have. And I do have some exercises on the Seaborn. This is much more easier than the Matplotlib exercises. And I thought it might be a good idea to use the Titanic dataset to plot some of these questions. This should be easy enough, and you'll make your own first plot. I have some useful resources for these plots. And this is a resource from from a professor at my university. And this is mostly in R, but R's ggplot has a very similar feel as Seaborn. So you can get ideas of the visualization concepts that go in to apply to in a Pythonic way, which is what I used it for, which is how I used it for this presentation. And I also have some references on the Matplotlib. This is a really good one, Matplotlib tutorials. If you're looking for some advanced plots in Matplotlib, this particular author does a really good job. And this has the source code for Matplotlib if you're interested in how it actually does behind the scenes. That's pretty much all I had. Do you guys have any questions? Any clarification you can provide?
Thank you, Nisha. Amazing. It's amazing. It's amazing. Thank you. Thank you. So if there's anyone that has any questions, we can take them right now. If anyone has any questions, you can unmute yourself and ask the question, and Nisha will be glad to answer that right now. Okay, Nisha, while some other people are getting their questions ready, for data science, what is like the most popular, maybe let's say 5 plots every data scientist needs to know? You know, sometimes this whole thing can be very, Python can be very overwhelming. So sometimes you just need to know, okay, if I have these 5 plots under my belt, I'm safe as a data scientist. Which one would you say?
So you're asking which one would you use more? Is that your question?
Yes. Which one would you encounter more in your work as a data scientist very frequently?
So for me, when I use more Seaborn than Matplotlib. Matplotlib comes at the end when I need more customization. Seaborn is the one I use pretty much for all my data exploration. And I'm sure most of the data scientists, if you ask them, they will be using Seaborn much more than Matplotlib. Matplotlib is to give that final touch to your plots. And I would think that's what most would say, and that's how I have been using in my experience as well. And most of Seaborn plots that I exploit is in the beginning section, which is the desk plot, giant plot, pad plot, bar plot, all of this. I do use a little bit of matrix plot. Cluster map is when cluster map actually uses the clustering algorithm behind the scenes. So if you are interested in those kind of things, this can actually become really informative. And here, this is just a quick demo to show with a very small data set, but then there are ways to, we are just scratching the surface. That's all I can say about this.
Okay, so I think this is used more when you are trying to do a correlation data set, so that you can be able to do a little feature engineering and drop some columns that are correlated, right? Before you.
Yes.
Yeah.
So to do cluster map or the matrix plot, we always need to have in a matrix format. Again, coming back to matrices. So we need to convert the data to be in a specific format to do these kind of heat maps. In this case, all I had to do was find the correlation. This is just a demo of how you can do. And in this case, I'm not looking at correlation. I'm looking at in each month, each year, I'm converting the table from a long format to a wide format. That's a common thing you would do with pandas as well. I think Yogita and Numpy, the before lecture, would have shown you a glimpse of how to do that. So essentially, all you need to know is you need to have a matrix where the internal number represents what this particular index does and what this particular index does. Here it means there were 112 flights in the month of January in year 1949. So if you can say that out loud, then you're ready to do a cluster map or a heat map. That's the easiest way to think about doing a heat map, essentially. Hope that makes sense.
Sure it does. Okay, so I'm putting up the link for downloads to download all of this stuff from Nisha's amazing GitHub. I'm just putting that right away.
Yes. Yeah, my GitHub is out there, and you can, that particular folder has both these notebooks, Matplotlib and Seaborn. If the direct link doesn't work, just go to that GitHub folder and you'll be able to download. Those are the only two big notebooks that are available in that folder.
Okay, great. So has anyone gotten a question? Anyone? Has anyone gotten a question? Okay.
I think I really did a great job, or I really did a poor job.
Yes. No. You didn't do a poor job, Nisha. Okay, so Kim is asking, have you ever used Seaborn with R?
No. So Seaborn has a very similar structure to the ggplot too. So this reference would give you the ones that you would use in R if you want to use the same kind of plots. And ggplot is like a combination of Matplotlib and Seaborn. So you have much more customization. So if you're going to be using R, I would say ggplot2 would be the library to go with, because you will be much more familiar with R essentially, and it is in that syntax. But I have never used Seaborn with R. No, sorry, Kimmy.